Good morning, boys and girls. Welcome to e-learning St. Vincent and the Grenadines. Today's lesson is physics, and I am your lecturer for today's session, Mr. Linsky Adams. All right. Now, what I have in front of me before I introduce the topic that we're going to be looking at are a few household items. I want you to take a look and see. All right. On the table, what we have here is a can of bop. We have a hammer and some nails. We also have a knife and a cucumber, and we also have a balloon with a screw and also a stick. These are items that you can find around your household. Now, question to you is, what do all of these have in common? Right? How can we apply science to each of these items that we can find in our household? And the answer to that question is the topic of pressure. Today's lesson, we're going to be focusing on pressure, in terms of pressure in solids, pressure in liquids, and pressure in gases. Now, before I introduce to you what exactly is pressure, let's look at some of these apparatus. Now, the first one, let's look at the hammer and the nail. In terms of any construction, we normally use a heavy object, which is known as a hammer, and a nail for fastening any item. Now, how do we place this nail when we want to hammer? Do we place it with this pointy edge, or do we place it with the flat head? Right? The answer to that question is that we normally place it with the pointy end and apply a force. Now, suppose we were to turn this nail upside down and try to pound it. If you notice this slight force I exerted on this nail, and it is stuck into the wood. Now let's see if the same thing can happen if I turn the nail upside down. If you notice, it cannot enter into the wood. We will come to the answer. We want to know why is that happening. Next one, we have a knife. If you can see, it has a sharp edge, and this side is a dull edge. We have a fruit, a cucumber. Now, how do we cut this cucumber? Do we apply the dull edge of the knife or the blunt edge of the knife to cut it? Or do we use the sharp edge? If you notice, as soon as I turn to the sharp edge, the blade went straight into the cucumber. But with the blunt edge, there is no penetration. What about the balloon? If you look at the balloon is a nice party favor that is filled with air. Good? We could squeeze the balloon, it can compress. We could put any object on it, and it can compress as well. Now, according to the amount of force we apply on it, it can compress even more. Let's say we take a cylindrical shaped object. If we apply it with this flat end, we notice this side is the biggest side of the cylinder, of the cuboid, and it can be compressed. What about if we apply the same force and turn it on this side? Do you notice anything happening? It can be compressed even more. Now, let's say if we try to use a screw. We use the pointy edge of the screw, and we apply the same amount of force that we were using with the cuboid. What do you think is going to happen? Woo! Explosion. Last one. This we have is a kind of insecticide, right? Bop. Now, how do we use bop? We simply press down on the nozzle, and what do you think happens? We have a compressed gas escapes this can. Right? Now, what I want you to understand is that all of these demonstrations that I just did actually explains the concept of pressure. So that's the first thing we want to understand, is that when we apply a force and that force goes over, is applied onto any surface, that we could have what is known as pressure being exerted on that object. Whether it be a solid object, or we would go into looking at gaseous object and liquid objects. So our first thing that we want to understand is the definition of pressure. That pressure is defined as the force acting normally per unit surface area. right? Force acting normally per unit surface area, and if you check this this term, it uses this term uses 2 points. It uses the force and the surface area. Now the key word there is normally. It means that the force must be acting at perpendicular to that surface, right? It must be acting at 90 degrees to any surface over which it acts, right? And the surface area we're referring to is the point of contact. So for each surface area of contact for any object acting on it, we want to see the force that is exerted, that is referred to as the pressure. Now, in this case, we want to understand that pressure and force are not the same term, but pressure is influenced by the concept of force. So, given that definition, we come up with a formula. A formula is derived that pressure is equal to force over area. Just the normal force over an area of contact. Good? Which is the total surface area. So this is the first formula that we will introduce to you for pressure, which uses a symbol notation of common P for pressure is equal to capital F for force and a capital A for area. Good. Now, with every formula there is a derived SI unit, meaning a unit that is understandable to be used throughout all of science. So it's the SI unit, which is referred to as Pascals. The SI unit of pressure is Pascals. However, we can realize that force can be measured with 1 unit, and area can be measured with also another unit, where force is normally measured with newtons, that's the SI unit of force, divided by the SI unit of area is meters squared. So, just like how we will derive a formula, we can derive the unit as well. So, in deriving the unit of pressure, we realize that newtons divided by meters squared give us the Newton per meters squared, written in this format or written as Nm to the negative 2 in indices. So what we want to understand is that these units are actually equal to the SI unit of pressure, which is Pascal. So 1 Pascal is equivalent to 1 Newton per meter squared. So in writing any answer that you ask to state the value of pressure, you could either state your answer in Newton per meter square, or, which is recommended, always state your values in SI unit, which is Pascals. Good. Now, what we want to see here is that pressure can be exerted in different states of matter. We have pressure on solids, pressure can be in liquids, and pressure in gases. That is why we're going to look at that today. So the first thing is pressure in solids. Now, as you know, we already established that pressure is the amount of force per unit area. Now, in the case of solids, we say that there are 2 main factors that influences pressure in solids, which are forces, or the force applied, and 2, the surface area of the point of contact. Right? As you can see on the slide. So the first one, it says that pressure is directly proportional to the force applied. Pressure is directly proportional to any force that is applied. Now what that means is that if we increase the amount of force that is acting on any object, it causes an increase in the pressure. Right? So as you can remember, when I use the hammer and the nail, if I pound the nail even harder, you're expected to pierce into the wood deeper, right? So it means that there will be an increase in pressure. Secondly, you have surface area, that pressure is actually inversely proportional to the surface area. Now what that means is that the smaller the surface area, the larger the pressure is going to be. The smaller the surface area, the larger the pressure, or inversely you can say that the larger the area, the smaller the pressure. And that can actually be looked at from this formula. As you know, physics is related to maths. Physics is the father of maths. Good? So what you can see here is that area is the denominator for this equation. The smaller the denominator, the larger the quotient is going to be. The larger the pressure is going to be here. For instance, if we keep the force constant, let's say we keep the force of 1 Newton, and we look at the area is 4 meters squared, compared to if we had a force of 1 Newton acting over an area of 2 meters squared. Which of these fractions is the larger? And we're going to realize that 1 over 4 compared to 1 over 2 shows that the smaller area of 2 meters squared is actually larger than, well, gives you a larger pressure than when the surface area is 4 meters squared, which will result in a smaller pressure. Okay? So that looks at the two main factors that influences pressure in solids. Good? So that's all you need to know for that aspect. Next, we're going to look at pressure in liquids. Now, I want you to follow me with this explanation. Now, we want to say that fluids can also exert pressure, and that the pressure due to liquids is due to the weight of the water above a given point. Now, if we were to go in a pool and we dive down to any given depth, let's say we have a pool here, and pool is filled with water, and at any given depth, let's say we have an object here, this is a diver at this point. What you're going to realize is that there is a column of water directly above that diver. And this water itself has weight. All this water has weight which is acting down on this diver. Okay? Now, let's use the same formula for finding pressure. How do we find the pressure experienced at this depth where the diver is located? Now, it says that pressure is equal to force over area. Now, how can we measure the weight of this water column that is directly above the diver? Can we take this water out of the pool and put it on a scale to measure it? No. There must be some other way in which we can measure the weight of that water. So we know that force is contributed by the weight of the water. So to find weight, there's a general formula for finding weight, which is mass times gravity, right? Which is mg. So it means that we must be able to find the mass of this water. This is showing the flow of the formula. Now, a keynote to understand in physics, anytime we're dealing with a liquid, we always must consider the density of the liquid. Now, so it means this term, mass, there's another formula for finding mass when you're dealing with a liquid, mass of the liquid. Good? So where mass is actually equal to the density of the liquid multiplied by the volume of that liquid. So when we substitute this part of the equation into this general equation, we get rho v g over A. We can be able to determine the density of this liquid. We can be able to find the volume of this liquid. We know the gravity, which is a constant value. However, the area, how can we determine the area over which the water is in contact with the diver? Do we measure the area, our surface area? It might be difficult to determine that over where the water is covering our bodies. So, but this volume, and the area are actually related, where a general formula for volume is actually the area of an object multiplied by a height. This is in every formula that you can find where you want to find the volume of a shape. Good? So volume is actually equal to area by height. Let me write out the words there for you. So if we substitute this now into this general equation, we get that rho AHG is over A. And as you can see, that area can cancel area, and we're left with, I'm just going to rearrange it, H rho G is the formula for finding liquid pressure. So we can determine the depth, which is the height of the water column. Rho, we can determine what the density of the liquid is. Let's say if it is water, we know that the density of water is actually a constant value of 1,000 kilograms per meters cubed. And gravity is a constant value of, well, at CSEC level we use 10 newtons per kilograms. Good? So we can find H, we know rho, and we know G. So that is how we use the formula there for finding pressure in liquids. So it shows you now, if you look at the slide, it says the factors that actually influence or factors affecting pressure in fluids is the depth and also the density of the liquid, which shows that the depth is directly proportional to the liquid pressure, and also that the density of the liquid is also directly proportional to the liquid pressure. When we say directly proportional, it means if one quantity increases, the other quantity is going to increase. So if we increase the depth, further down we go, we're expected to increase the liquid pressure experience. If we increase the density of the liquid, we are expected to increase the pressure due to the liquid. Good? Gravity remains constant. Okay? So that explains the two main factors affecting fluid pressure. So as you can see here, that the general formula is the height multiplied by the density multiplied by the gravitational acceleration, which uses H rho G. So in that formula, you just remember that H can mean the height of the water column or the depth below the surface of the liquid. Good. Now, some factors influencing liquid pressure here. These are the factors that we go through each of them. It says that pressure does not depend on the shape of the container. It doesn't matter any shape that you put the object in. It only pays attention to the density of the liquid or the depth below any surface. So if you look at the middle diagram there, we have different vases of different shape. What you're going to realize is that even though all of them have the same height, that at the base of those vases, they're going to have the same pressure because the water level is all the same height. Okay? The second point there is that all points on the same horizontal level in a liquid at rest have the same pressure. So what that means is that the pressure at any height or any depth across a horizontal level is always going to be the same. So the pressure at the surface of the liquid horizontally is going to be the same value. So if the pressure at that horizontal point is 50 pascals, if we go across on a horizontal plane, the pressure is still going to be 50 pascals. If we go down to a depth of 20 meters in a pool, and I am here, I experience a pressure of 100 pascals, another person over at the same depth is going to experience the same amount of pressure there. Third point is that pressure acts equally in all directions. So pressure at any depth is acting upwards, to the right, to the left, downwards. It's acting at the same value is being applied equally in all directions. In a few minutes, I'm going to explain that point. I'm actually going to demonstrate that to you. Next point is that pressure increases with depth. All right? I would have gone through that. And lastly, we have that pressure is directly proportional to the density of a liquid. So that is what we want to understand. These are the main points that influences pressure in a liquid or pressure due to a liquid. Now, to look at that, I'm going to do a demonstration here for you. Right? Now, if you look at the slideshow, you can see a diagram there that shows a bottle that has 3 openings. And that's different layers. You're going to see that the further down you go, you're going to have the water shooting out even further due to pressure. Good? So we have here set up 3 bottles. And each of these bottles are filled to capacity with a liquid. Good. And these bottles actually have an opening at different heights, right, or different depths. Now this first bottle, bottle A, has an opening which is 10 centimeters from the top of the liquid. Bottle B has an opening which is 16 centimeters from the top. And bottle C has an opening which is 28 centimeters from the top. Now what we're going to quickly do is to determine, we want to prove that diagram, and we want to actually see how far each of these actually go. Right? So firstly we have bottle A, which is 10 centimeters. We want to measure in centimeters how far it goes. Bottle B, which is 16 centimeters. And bottle C, which is 28 centimeters. We want to see how far that water shoots. So, I'm placing it here. So you're going to look quickly, you're going to see. Right? That is approximately 18 centimeters. Everybody can see how that shoots out there. I have a ruler here, it measures approximately 18 centimeters. Okay? So it goes about 18 centimeters from its initial point. Let's see bottle B. Let's see the pressure exerted down. So this hole is 18 centimeters from the top. Good. It's about 23 centimeters. You can see how much further this one goes. Bodies can see that. Right, so I said about 23 centimeters. And let's see the last one. This one actually has a hole at the base of the bottle. But you can see this one, right? So this one actually goes about 32 centimeters initially, right? And as it is open, the water goes down, the level of the water goes down, so you can see the distance will now start to decrease, okay? So I said that one is about 32 centimeters, right? So that simple experiment proves that with the increase in height, that the pressure is going to be larger, that the water shoots out even further away from its initial location. Now, that bit of knowledge is actually how certain devices are made. For example, here in Simvinsu, we use a black drum in terms of collecting water. And you know, at the base of the black drum is where you'll find the opening or the pipe top. So where you get maximum pressure of water that will go to your household. Okay? Now we're going to look at pressure in liquids. Actually, sorry, we're going to look at a question first. Now the question, as you can see, states a 15 kilogram rectangular block with a length of 70 centimeters and width 40 centimeters rests on a table. What pressure does the book exert on the table? Right? So we want to determine what pressure would be exerted on the table. And we have options there, whether A, B, C, or D. So let's quickly work it out. Now remember, the question is asking for us to find pressure. Right? And this question is related to a solid, so we have to know what formula do we use to find pressure in a solid. And that formula is force over area. The question gave us the mass of 15 kilograms, and it gives us the area of contact in terms of the dimensions, where we know that area is equal to length times width. So it means that it is the 70 centimeters multiplied by the 40 centimeters. Now, the question didn't give us the force, But using the mass, we can be able to get the force, right? Because in this case, it is due to the weight of the object. So the force is actually due to the weight, which is mass times gravity. G is a constant value, which is always 10. So that value there is going to be 15 kg multiplied by 10 kg. 10 newtons per kilogram, sorry. Area. Now in this case, something I must let you know. Every time you do a formula, you must make sure that the values are in their SI units. Area, the SI unit of area is meter square. The value actually gives you the dimensions in centimeters. So my recommendation is that you firstly convert the centimeters to meters first before you get your area in meters square. So to convert centimeters to meters, we actually going from a smaller unit to a larger unit, so we divide. And we're going from centi back to the unit value, so we actually divide by 100. So it means that we're going to divide each of these values by 100. So it means that we're going to have 0.7 meters multiplied by 0.4 meters. Good? Which gives us a value of 0.28 meters squared. Now suppose you didn't know how to convert centimeters to meters. Suppose you want to find out you did it in centimeters square. Suppose you found your answer in centimeters square. Then you will have to learn how to convert centimeters square to meters square in order to do this calculation still. Now, centimeters to meters square, it follows a simple, just like how we learned this, is a simple conversion. To know how to convert centimeters to meters is that we divide by 100. And because we're looking at the power of 2, which is squared, it means that we're going to square this operation. So it means that we're going to be divided by 100 squared, which is 100 squared is actually 10,000. So it means that we're going to divide that value by 10,000, which gives you the same answer of 0.28 meters squared. Good? 0.28 meters squared, and that gives you an answer of 150 divided by 0.28, where your answer should actually be C, all right? Which is 53.6 pascals. Okay? Your answer should be C there. Let's look at the next question. Number 2. It says a closed rectangular container with dimensions 4 meters by 5 meters by 6 meters is filled with water. What is the pressure exerted by the water on the bottom face of the container? So read that question again and see what it is. Let's see what's the main thing it's asking for. Good? So it gives the dimensions of the container. Now, anytime our dimensions are given, they're always given length times width times height. So it means that it's 4 meters by 5 meters times 6 meters. Right? So that is 4 and 5, and the height is 6 meters. So this container is filled with water. All right? So the question asks, what is the pressure exerted by the water on the bottom face of the container? So we want to know what is the pressure at the base. What is the pressure at this base here? At the bottom. Now, it is asking for liquid pressure. So it means that we have to use the formula for finding liquid pressure, which is H rho G. Good? H, given in the question, is 6 meters. Density, because it's liquid, it means that's the height of the liquid, density of the liquid, and gravity. I gave you what the density of the liquid is before. Everybody remember? It should be 1,000 kilograms per meters cube. Good? And then gravity is 10 newtons per kilogram. Right? So in this question, because the values are in meters, we use this unit of density of kilograms per meters cube. Okay? If the values were in centimeters, then we would have used the density in grams per centimeters cube, which is actually equal to 1 gram per centimeter cube for the density of a liquid. Okay, in that unit. So 1,000 kilograms per meter cube is actually equivalent to 1 gram per centimeter cube. So let's continue with the calculation. So we have 6 multiplied by 1,000 multiplied by 10. So we end up with 60,000 pascals. All right, so answer there is 60,000 pascals. Now I mentioned that the SI unit is pascals. Now if you have a large number like this, you know, we can make this number smaller. All right, that's where the prefixes of units come in, where you can learn how to convert pascals to, let's say, kilopascals or megapascals based on their scientific notation. So if we look at this, we can turn this number into 60 by 10 to the third power, whereby 10 to the third power actually represents kilo. So it can become 60 kilopascals. Okay, so this is another way for writing that answer. All of these are correct ways of writing the same answer. Okay? Now we're going to look at pressure in gases. We want to know what contributes to pressure in gases. Good? Now it says that the pressure of solids and liquids can be attributed to their weight, but the weight of gas is very small compared with that of a solid and of a liquid, because you know we can't really take air and measure it on a scale, right? But what we're going to do, if we trap a gas into some container, for instance, if we trap gas in this balloon, what really causes the balloon to expand is the pressure exerted by these gas molecules inside the balloon, right? Now, what happens is that these gas particles have so much energy that they're always moving, that they're going to run from one end of the balloon over to the other end and back continuously. Now, as these small particles travel at various speeds, they're going to collide with the walls of their container. And as they collide with the walls of the container, they apply a force onto the wall. And that force, based on the small area of contact, actually produces a pressure, right? So therefore, you have a pressure being exerted within this container. So is the case of the balloon blowing up, or the case of a bicycle tire that you pump air into, or the case of a car tire that you pump air to, that you have the pounds of air being exerted over a certain area. So another example, another unit that we don't use in science, but is PSI. PSI means pounds per square inch. That's another unit of pressure. Okay? So what you can see there, it says that the molecules of a gas are at constant random motion as the molecules move around. They strike the walls of the container and rebound from it. At each collision, there is a change in momentum. Change in momentum meaning the mass, the change in velocity. The change going from one direction to another direction. That's where momentum is change. Now it says that this change in momentum per second results in a normal force on the inner walls of the container, and the force acts per unit surface area, hence resulting in a pressure on the walls. Okay? Now we're going to be looking at atmospheric pressure. Now atmospheric pressure is an example of gas pressure. There's another term known as air pressure. Now it says that the atmosphere is actually a combination of many gases, and which causes and this causes a weight which causes atmospheric pressure, right? So air is all around us, and the air is actually applying a weight down on our body, right? And that weight down on our body causes a pressure on us. Okay? And what I want you to understand is the atmosphere is made up of many different layers, right? We have some of the layers identified there, right? And the deeper or the lower down in these layers you go, the more the pressure is going to be increased. Now, these layers start from the edge of space down onto the Earth's surface, where the Earth's surface is the base of the atmosphere. So you're going to expect that the highest atmospheric pressure is going to be located on the Earth's surface. Right? So it says that the atmospheric pressure is the result of the weight of all of the gases in the atmosphere, and as you go up, the air gets thinner, the density decreases, and the pressure decreases. So it means as we come down now, the pressure is going to decrease. Now it says that once there is air in contact with a liquid, the pressure on the surface of the liquid is actually equal to the atmospheric pressure. Right? So anything that is open to air is experiencing atmospheric pressure. So a glass filled with water, a pool with water at the surface is actually causing atmospheric pressure. So when you go deeper down into a pool, you're actually experiencing pressure due to the atmosphere and pressure due to the liquid. Good? Because atmospheric pressure is always acting down on us because we exist in the medium of air. Now, atmospheric pressure actually has a constant value of 101,000 pascals, which is also referred to as 101 kilopascals. That is the value we use at this level, at CSEC level. Right? So that's a constant value. Right? Now, before we go to that, I want to show you a demonstration here, where it shows a point where we talk about pressure acts equally in all directions. Good? So, and to tie in the case of atmospheric pressure. Now, we have a glass here that is filled with water and a lid that is actually over the glass. Right? As you can see, atmospheric pressure is actually acting down on the surface of the lid at this point. Now, if we were supposed to go direction, so we can see, we actually have a suction there that the lid, it doesn't remove because atmospheric pressure is actually acting upwards. Okay? Now, we want to understand that pressure and force can act in any system. Right? We want to look realistically how we can use the concept of pressure in any device that we have around. So we have pressure and force in a liquid, where it says that the pressure in a liquid can be used to transmit a force because of the following properties. Right? And in this case, we're going to explain that of the hydraulic braking system in a vehicle, or hydraulic jack, or even rockets, how they actually use. Right? Now, the first property is that liquids are incompressible. It means now that the volume of a liquid cannot be decreased even though we apply a force on it. So an example of that is if we look at the balloon, if we try to squeeze the balloon, when we squeeze one end, the other end pops out. Right? That is incompressible. You can't compress it down to a smaller volume. Next point is that liquid pressure acts equally in all directions at the same level. It acts equally in all directions at the same level. And the third point to tie it in is that if pressure is applied to a trapped liquid, it says that the changes in the liquid pressure is transmitted instantaneously and uniformly to all parts of the liquid. Good? It is the force or the pressure is transmitted instantaneously. So as soon as we press on one side, that pressure is transmitted to another side of the system instantaneously. Good? So, as I mentioned, that this methodology is actually used in the development of certain apparatus or certain devices. For example, a hydraulic lift. Right? So if we apply a force on one side, we can lift up huge vehicles. Right? Now, it actually uses a law which is known as Pascal's Law. As you can see, it says that the pressure applied to any point of a fluid in a closed vessel is transmitted equally to every point in the fluid. Right? So it means that if we apply a force at one point, so in the case we have one piston and a second piston, a smaller piston and a larger piston. So if we apply a pressure at piston 1, that the pressure exerted at piston 1 is going to be transmitted equally throughout the liquid. Okay? And be exerted up at piston 2. So in a case for most of you who know about a vehicle, like when you drive a vehicle, you have to, and you want brakes, you have to fill up the brakes line with the brakes liquid. Because if the brakes line is not filled to capacity, then there will be air bubbles in it, and pressure would not be able to pass through the air bubble, right? So therefore, there's a case where you say that you're losing brakes. So you hear the term that say you have to bleed the brakes, meaning that we want to get rid of all the air bubbles out of the line. Because as soon as we mash the brakes, that pressure is transmitted throughout the liquid or the brakes liquid all the way to the brakes calipers to squeeze the wheel to cause it to stop spinning. Okay, so that's the methodology there. Now, I'm just going to show you a slight demonstration here of how what we mean when we talk about air being trapped and what is going to happen here. Now, I have a bicycle pump that I'm going to pump some air into this pipe network, and as a result, it's going to cause this bottle to be lifted up based on the pressure inside. Good? So it is going to cause, you tell me what you think is going to happen here. All right, so I'm going to pump pressure into it, and you have to look quickly. Everybody saw that? I'll do it one more time. So I'm applying a force downward in the bicycle pump. This is my piston 1 here. I'm going to be compressing air in this pipe network, and therefore this piston also has a second area, and it's going to cause an increase in pressure there, or the same pressure is going to be exerted. So let's go. So everybody could see there. Right? So finally, we're going to look at an application of this. The question. It says the input piston of a hydraulic jack has a cross-sectional area of 5 centimeters square. The larger piston has cross-sectional area of 500 centimeters square, and we want to find out what force applied to the input piston will raise a car of mass 2,500 kilograms. Right? So the key word in this question is that we're looking at a hydraulic jack. And because we're looking at a hydraulic jack, we're looking at the concept of Pascal's law, which states that the pressure input is equal to the pressure output. So in every question, you have to look for a keyword. So it means that this is the formula that we're going to use. The pressure input is equal to the pressure output. So the pressure input looks at the force at piston 1 over the area at piston 1, which will be equal to the force at piston 2 over the area at piston 2. So the question states what the area is. The area 1 is 5 centimeters square. The area 2 is 500 centimeters square. And it says it raises a mass. So the mass of the car that it raises is actually 2,500 kilograms. So we're going to use this to find F2. Good? Now, as I mentioned, anytime we use mass is to contribute to find the force, where force is equal to the mass times gravity. So it gives us 2,500 kilograms multiplied by 10 newtons per kilograms gives us a force of 25,000 newtons. Good? So the question asks us to find F1. So we're going to substitute all our values into this equation. 5 centimeters squared over 25,000 newtons over 500 centimeters squared. Now, there's a key point about this type of question. Right? You know, initially I told you that area, every time we use area, we must convert them to their SI units. Good? However, in this type of question, once the units are the same, we do not have to convert them to the SI units. Let me show you why. We want to find F1, so we have to make F1 the subject of this equation, so it means that we have to move the term that is not that least affects it, which is the 5 centimeters, so we're going to carry it over. We're going to cross multiply. So we end up with F1 is equal to, so because 5 is divided on this side, when it goes over, it multiplies. All right, I'm going to put the unit there. 500 centimeters squared. So with the unit there, as I was saying, why we do not have to convert the centimeter square to meter square? Because in this case, this centimeter square cancels this centimeter square. The units cancel each other. If we had converted them to meter square to begin with, the same thing is going to happen where meter square is going to cancel meter square, and the ratio of these values, 5 over 500 and 5 to the negative by 10 to the negative 4 over 500 by 10 to the negative 4 is the same ratio. Okay? So we cancel out that 0, 0, and do I have them in the right place? Right. So our answer there now, 5 cancels 5, so we end up with 250. Oh my gosh. Right. Our answer there is 250 newtons, which would have been our option C in the question. Right? So, in today's lesson, our